A very good afternoon to all of you. I am Ella, welcoming you all on behalf of eMobility Plus and First View Group to our webinar on modeling thermal runaway and abuse in batteries. I take the pleasure to thank our partner ComSol for their immense support to organize this event. First, I'd like to introduce our session expert, Dr. Rustam Shekhar, Technical Specialist, ComSol. Dr. Rustam Singh Shekhar is a technical specialist at ComSol, specializing in electrochemistry and battery simulation. Received his PhD in Energy Science and Engineering from IIT Bombay, Masters in Chemical Engineering from IIT Hyderabad, and Bachelor's in Chemical Engineering from MIT's Gwalior. His expertise include electrode microstructure and cell and pack level modeling. So before we dive into the presentation, let me give you a quick overview of what to expect from today's webinar. As we know, one of the main factors influencing the safety of lithium-ion batteries is thermal runaway and its cascading effect through the pack. Thermal abuse conditions pose significant risks to battery function, often leading to severe damages. To predict and mitigate thermal runaway and comprehensive understanding of various physical phenomena is important, which includes encompassing chemical reactions, heat transfer, pack design, and fluid flow within the cooling system. This webinar will explore how to use multiphysics modeling to accurately predict thermal runaway and simulate thermal abuse conditions in batteries. After this, we'll have a Q&A session where you can ask your questions to our expert. But here I would like to make a small request. Attendees can post their questions in the Q&A box and our expert will answer those questions at the end of the session. But before starting the session, we would like to play a small video showcasing what ComSol has to offer to the automotive industry. I request my team to kindly play the video.
Developing designs and performing experiments virtually is both cost and time efficient. With ComSol multiphysics simulation software, you can be sure your results accurately represent the real world. By studying multiple physical effects on one model, no matter the order in which you combine different physics, the software handles them together and solves the mathematical and numerical model equations and provides you with the model results. The entire simulation process takes place in the same software environment. You only need to learn one workflow, no matter the physics involved or the nature of your experiments. Depending on the scenario, you may want to model single physics, one-way multiphysics, or fully coupled multiphysics. The ComSol software offers all three, and the true advantage of ComSol multiphysics is the ability to model unlimited multiphysics, where all physics in a model interact, affect each other, and together influence the model results. If you need to add any physics, including your own equations, to your model, you can. The application builder in ComSol multiphysics gives you the tools to build your own simulation apps. The startup wizard and drag and drop functionality help you quickly turn your models into simulation apps with customized user interfaces, restricted inputs and outputs, report generators, and more. This way, you can spread the advantages of simulation to colleagues and customers by compiling your apps as standalone executables via ComSol compiler, or by making them accessible by web browser via ComSol server. Understand, predict, innovate, and optimize your processes and designs with ComSol multiphysics.
Thank you, team, for playing that. May I now welcome our session expert, Dr. Rustam Shekhar, on the screen. Over to you, Dr. Rustam Shekhar.
Yeah, thanks, Ala, for the introduction and setting up the context. So for now, we'll go through the presentation that we have, and then later, follow to that, we can take up the questions as a host mentioned. So, yeah, I hope the screen is visible to everyone. So now we can see today that how modeling can help you to avoid the thermal runaway, and if there's any abuse conditions in batteries, so how those can be handled. Uh, just to give you a summary that what we are going to cover today, it will be about the battery design module that we have, And in this battery design module, you will be able to handle the cell models, pack level models, thermal management of it, and the studies that you can have. So when we combine cell level models to a pack level model and then add the heat transfer to it, that will give you the complete scenario of a battery model where you can perform the different test, which is the thermal runaway test, where you can induce the failure of one cell and see the propagation. Or else, if you want to predict the failure of that particular cell, then that also can be done in the great detailed manner in a cell level model by using the detailed electrochemical model, which we call Newman's model. So Newman's model will give you the detailed picture about at a cell level, and then when it's going up to the pack level model, then you can perform that pack level model, the propagation part of the thermal runaway. So, and then these kind of different strategies, when you want to make to prevent thermal runaway, then you may be interested to do the time dependent studies, some kind of cyclic voltammetry, impedance plots, and parameter estimations. All these different type of studies give you freedom to perform your modeling studies in the great detailed manner. So before going for the presentation, I just want to know that how many of you are familiar with COMSOL, and then according to that only we will just try to go ahead to know and understand the the people that we are talking to. So I request you to request the host to launch that poll, which talks about the first. Yeah. So please register your responses in this poll.
Sir, if you could just stop the screen share for the polls to be visible on the screen.
Okay. So I hope now it's visible.
Yes, I'll just publish them. Yeah.
Yep. So now, if the attendees can let us know that are they using tools COMSOL for their applications, or are they using different tools? They came to just see what's going on and then just came by their personal interest. That will help us to shape our presentation, and then accordingly we will try to explain that what really we can have we can do in this tool regarding batteries and thermal runaway scenarios. Yep.
I'll screen the second poll question now.
Yeah, thanks. I think as we can see, people are evaluating tools for their ongoing applications. And okay, so let me just share the slide again to go ahead with the presentation. Okay, so now we will briefly talk about the battery and module. So which will offers you the functionality to model the different kind of batteries in a single unified environment. When we talk about batteries, we are not specifically talking about the lithium batteries. It involves all batteries which are available in market. They can be lead acid batteries, which are the conventional one. People are using them for the long period of time. They can be very popular one like lithium batteries, or else there are some other batteries like metal hydride or the vanadium flow batteries. So these flow batteries are the new trend where if you want to go for a large scale storage for the charges, then you can use these flow batteries. So basically, if it can handle all kind of major battery chemistry, so whichever device is governed by the electrochemical phenomena, you can model in the battery gen module. Basically, it will follow the Nernst-Planck equations, which is the first principle, and it will model the kinetics in any chemistry, which is porous electrode or the solid electrode. If the electrode is porous in nature or else they are just flat surfaces, you can model in the COMSOL multiphysics. When you model those scenarios, then you can perform the time dependent studies, including transient simulations, impedance plot, cyclic voltammetry, or as any kind of charge which are cycling that comes under the time dependent studies. And when you simulate those different scenarios in battery design module, then you can add the other physics as well. So if we take an example of a battery system, so then you'll start with very fundamental physics, like you are having a butler Volmer which is giving you current, and then from there you keep on adding the mass transport, then you add the heat transfer to it, that will give you one battery system. And if you're designing any kind of flows cooling mechanisms around it, that will include the fluid flow, and in batteries during the operation due to charging and discharging or cycling, you will see thermal expansion and contraction due to that thermal stresses or structural stresses will also will generate it. So that kind of scenarios also can be modeled. So now we have one fundamental equation. From that fundamental equation we can add the multiple physics, and then you can go for a multi-physics kind of scenario for the modeling batteries and the different kind of analysis like thermal runaway and the capacity loss. So now if you want to model the batteries, so then there can be multiple approaches that can handle the battery system. So the people who wants to work on the fundamental level, they want to know the failure mechanisms, or they want to know the why this is why this battery is getting failed, and they want to model the abuse scenarios. So in that case, they can go for the detailed electrochemical model, which are the heterogeneous or the homogeneous models. So in these heterogeneous models, if you want to model electrode, and then you can model the very similar to the experiments. So in experiments, what you do, you just mix two powders, make a slurry and paste it. So that particular slurry or the layer will have the particles arranged in a random manner, and then you can fill the electrolyte in between that. Similarly, you can see this thing here as well, where let me just open the. Okay, so similarly here you can see the particles are arranged in a random manner. They have some kind of particle size distribution, and then there is an electrolyte filled in between that. So, so basically, we are modeling the mass transport, and then there will be mass transport of second phase where the particle will go inside, lithium will go inside this particle, which is intercalation. So we are modeling the mass transport, intercalation, and then reactions happening on the surface. So this way, you can model one electrode in a detailed manner. Here you can include the thermal effect, structural effect. If any kind of flow like gas generation is there and you have a two-phase flow, then you can add that as well. So how it is helping into the thermal runaway scenario, so where let's say you are having a particle lithium plating into these particles. So then you have electrochemical reaction happening on the surface, and then if there is a difference between the mass transport in the bulk, which is an electrolyte, and mass transport in solid, which is intercalation, then you will start accumulating the lithium on the surface, and that will grow as a dendrite, and it may puncture your membrane. So that scenario may occur at high C rate conditions, at low and then low temperature conditions. And both conditions, the difference in mass transport is there, and then you will see the dendrite growth or the particle plating will happen. So if you want to go into that detail, where you want to know how particle lithium plating is happening, how gas formation is happening, how SA formation will affect the mass transport. So all these detailed scenario can be modeled in heterogeneous models. So there you can identify the abuse conditions and abuse scenarios from the battery system, specifically in one particular electrode, and that can be done for the both electrodes. So you will have a single battery where both electrodes, current collectors, and membrane and separators are placed, and you can do one detailed analysis. So in cases, let's say you are not interested into the particle level detail, you just want to know in overall sense how battery will perform and how these failure scenarios will get triggered, then you homogenize it, and then again still can account for the intercalation. That will be done by this 1D particle diffusion, which is intercalation, and which follows the Newman's model. And then you can design the single cell, or you can stack them and make a battery pack. So in this particular homogeneous models also, you will model the homogeneous electrode and do the design analysis, performance analysis, and the aging and many more. So when we say more, that includes the internal short circuit or external short circuit. And lithium plating also, and gassing as a formation, all can be designed here. In some cases you want to model the particle cracking, so that will be handled by the heterogeneous and homogeneous models. And the difference that you can see between heterogeneous and homogeneous will be, here you are in homogeneous, you are not modeling the particle, you are just accounting for the intercalation. But in heterogeneous, you can exactly take the same electrode geometry and work on that. So you can import the 3D geometry tomography data, and then you can work with that. So this is how you can work with homogeneous and heterogeneous model. And there is a one more approach with a single particle. So if you are not working at very high seeded conditions where mass transport is a limiting rate, so then you can just work with single particle models and see the detailed electrochemical phenomena to see how gas will get generate for form in the electrode, how lithium plating will happen. So this scenario can be accommodated by using a single particle model. So the single particle models generally are the 0D model, and so they won't involve any kind of geometry with them. So when geometry is not involved in this scenario, so that means this model will be very fast to solve. So then you can create a battery pack, or you can use it for the real-time parameter estimation, or as in onboard applications. So the single particle models can be used to see how cell is performing, and based on that, if you figure out any kind of failure mechanisms like overcharging, discharging, and temperature rise unevenly, then the single particle models can be deployed. So slowly we are moving from the electrode to the pack level model, and then now you can utilize this lump parameter model, which is very important, specifically made for the battery pack, or else in the situation where you are not aware of material properties. So in Indian scenarios, what we see that people are not uh, in this scenarios, we can see this. The battery pack that if you are not aware of the material properties, so in that case you use this lump parameter model and then figure out the battery model. So first three approaches will require material property, and this lump model will require the experimental data with that. So this way you can cover the entire spectrum, where you start with electrode level model to a cell level model, pack level model, and in case you are not aware of material property as well, then also you can figure out the lump parameter model and make a battery pack. So when you go from the cell level electrode level to the pack level model, the complexity will decrease, and then you can go for the faster simulations. So this looks like a very reverse for information now, where we have bigger models, and they are very easy to solve and fast to solve. Now, once you know that which approach you need to take to design the this kind of scenarios, then you can start from the electrode level to the pack level model. It can go from 1D to 3D models, and then you can have the micro scale to the pack level scale model. When it comes to the coupling with the thermal systems, then you can have the Bundy detailed electrochemical model, or else 0D lump model, and couple them with a conjugate heat transfer, which will give you the thermal management models. And it will not restrict you to any size and shape of the battery. So then you can work with all size and shape of the battery, which includes the button cell, pouch cell, cylindrical cell, and the prismatic cells. So it will cover all kind of scenarios where geometry is not a constraint in this tool. Okay, so this particular slide will give you an overview. So if you want to account for the failure mechanisms, so aging is a one factor which will lead to the failure of the battery, which includes the plating, short circuiting, gas evolution, side reactions due to the surface area, loss of electrolyte, say formation, mechanical degradation, which means a particle cracking or crack formation. So all these failure mechanisms which are listed here can be incorporated, and if you know any other kind of mechanisms as well, so those also can be incorporated, and then make a detailed electrochemical model. When it comes to thermal management, which is the one more cause of the failure of the battery, so then you can perform the thermal management at the module and the pack level model, where we can incorporate the short circuit, which can be internal or external, and thermal runaway. So there is a violent chemical reaction that may happen after failure. So then the thermal runaway or thermal behavior after the failure due to the chemical combustion can be incorporated, and then you can see the propagation in the pack. which covers starting from cell level to see the abuse modeling, and then propagation part into the thermal management. So now, fundamentally, how it will approach the battery models. We told you that there is a multiple approaches, but how this approach will look like fundamentally. So you are taking care of the kinetics. You are working with thermodynamics. So this kinetic and thermodynamic pair will give you the feasibility and rate of the chemical electrochemical reaction. And then you add the mass transport and charge transport, which will be done by the diffusion, migration, and the convection. In case of there is any advection is happening, and you can account for the charge and current balance. That means it will be following the all conservation laws, and then you add the heat transfer to it, which will give you the complete picture, which we talked in the previous slide. So now we talked about the different approaches. So then both two different approaches or the three approaches can be compared, and then you can see how that can be handled in the COMSOL multiphysics. So here what we observe that we have one heterogeneous model, which are the detailed shape and the electrode and pores, electrolyte, everything is accommodated there. And there's a model which is homogenized, which account for the homogenized slab. So we can just take the real structure, make a model of it, and then these real structures can be converted to a slab, which is the homogenized phase, and create a model out of it. So when we compare these two approaches, heterogeneous and homogeneous, so they can give you same results, but they may have the different kind of outcome when it comes to the comparing both approaches. Now, we talked about the cell level failure. Now we can talk about the pack level models. In pack level models, what you do, you can take the lump physics models and couple it with the heat transfer. So, which is 3D conjugate heat transfer models, where you can assign the properties in an isotopic manner. So, properties are anisotropic and then correspond to the foil, electrode, and separator. So when properties are not isotropic, in that case, you can use this heat transfer module and design the thermal management system. So in this case, if you want to model the hundreds of cells, so they can be modeled. Here, this particular model, you can see we have 100 cells, and they are showing that the temperature difference is around 6 degrees in this kind of scenarios. There is one more approach which you can have, where you can solve for the 1D detailed model and do the 3D conjugate heat transfer. So though this particular model is a liquid cooled systems, where you can have the channels between the cells and then have the coolant flow in this, so to do the thermal management part of it. So here it is one in Numis model, 3D conjugate heat transfer, we are including 6 batteries and 3 plates for the cooling channels. This way you can model the hundreds of cells in this particular kind of approach. So we have both two approaches. One approach is where we locally generate the source in the lump physics models, or else we can just take the 1D Numis model. You can take this Numis model in 3D format and do the thermal management part of it. But again, it will cost you computationally very heavy. So that's why we just prescribed you two different approaches, which are the computationally feasible as well. So they are less expensive and give you the similar kind of results, which will give you the 3D, will be given by the 3D Numis models as well. So now we can perform the cell level simulation, pack level simulation, and add the heat transfer to it. And this will give you the similar results, which is available like in the 3D systems. So now, so this was the basic intro that we are having. But now I want to know how many of you working on the what level. So people may work on cell level, people may work on the pack level, and they are very only interested into the failure mechanisms or the other they are preferring. So I request the team to launch this poll so we can get the responses, and accordingly we can have a more discussion on on the option which people are interested more. So please launch this poll. I just stop sharing so we can launch the poll.
Sure.
Yeah, so these poll questions says that if you based on the different kind of strategies that you want to work on, uh, we talked about the cell level, pack level, and the thermal management part of it in a brief manner. Now we can take the option which is more like family, more popular amongst you. So the topic which you want to talk about more.
Shall I share the third question now, sir?
No, so that I think it will be for the at the last of last at the last.
So I'll just hide it from the stage. People can still answer.
Yeah, sure.
During this.
Okay. So now let's go back to the presentation. Okay, so now after this second poll, what we can see. Okay, so now after this poll, I just want to brief you or give you a flavor about if let's say you want to work on the cell level failure mode. So there we will talk about four different case studies that will give you a decent picture. So let's say in the batteries, when you assemble one battery, then the first thing which you see, which is a desired behavior, is the SA formation, which is solid electrolyte interface, which is being formed. So your electrolyte will get consumed, and it will make a layer on the electrode surface. So initially, it is required to prevent the highly exothermic reactions. But later, when it will keep on growing, then it affects the battery performance, and it will increase the internal resistance into the batteries. So in that case, we want to model this, and because of the consumption of electrolyte, we want to know how capacity will get degraded. And how this is related to the thermal runaway, generally we see when you have the high IR losses due to the internal resistance increase, we will produce more heat, and based on that, we will create the scenario which is more prone to fail. So that means if you are accounting or we are checking how SA formation is happening, then we will always keep on check that how these things will this particular kind of failure mechanism will happen. So if you want to account for the SA formation, then we can take one homogeneous Newton's model, extend the SA formation, which is parasitic reaction. So the thickness of SA layer we will account for as a variable, and which will impact the film resistance, increasing on the particle surface. So in that case, the thickness is a variable, and then we can perform one CCCV condition where we have a constant current charging up to the 4.1 volt, and then we can discharge it with up to the 2.5 volt. So this way we can keep on charge and discharge the cell, and then observe the comparison of discharge curve with the different discharge curve. So as we can see, first discharge curve is available at more than 3000 seconds, and now when we go for the higher number of cycles, then it will go drop down below the 3000. That means while running the battery, we are increasing the SA formation, where we are losing capacity, and that is affecting the performance. That is increasing the IR losses, and then that is going more near to the failure scenarios. So this is the one comparison of discharge curve, and similarly we can just compare with the cycle number. So with cycle number, how I am losing my capacity. So from first cycle to the last cycle, which is the how the capacity is varying, and spatially variation also. So at what location I am losing the more capacity. So as we can see, which is expected that at solid electrode and electrolyte interface, we are losing more material. That means the reaction is more, and then we are losing more material. So this way we can analyze the SI formation in detail, and from there we can predict and see how this will lead to the failure of the batteries, which is increasing the which will help into the increasing the IR losses in the battery and battery pack. Now, if you want to take the one more use case, that we can see the mechanical degradation. In mechanical degradation, what we observe that, let's say your lithium intercalation is happening in this particular domain. So these particles will face some kind of stresses which we can visualize here, and based on the intercalation, your crystal structure of graphite particle will change. And so we will do, we will make a 1D Newman's model or the 3D detailed model, and we can extend this battery for the structural mechanics and see the, because of expansion contraction, how battery will perform. So then we can compare at different time at a different location how much stresses are getting generated. So this mechanical degradation again will lead to the more SA formation, and then we are losing more capacity. So this capacity loss again will help to increase the IR losses, and those IR losses again will give you more more degradation, and that will lead to more failure in the battery. So this is one more classical case. Now, if we move ahead, then there is a one more thing which harm the battery, which is lithium plating. So again, lithium plating, the same kind of approach we have taken, where we model the things in the 1D, or else then when we operate the cell at a different kind of charging discharging scheme. So we have a 2D Newman's model for lithium plating, and then in 2D model we just see how dendrite will grow, and you can see, because of the dendrite growth, when it will more prone to failure. So in figure 3 and 4, what we do, we just place one filament or the some kind of particle, and that, because of this lithium plating, if any kind of short circuit is happening, so then we can announce for that. And figure 1 or 2 shows that if my dendrite will grow, so what is the size and shape of the dendrite, and when it will touch the electrolyte, we will consider that is a failed cell. So either even grow of dendrite, or else the dendrite is already placed there, both kind of lithium plating scenarios that you can model. And this will give you one alarm where, let's say, if you are working at high C rate conditions and low temperature condition, and if your dendrite is grown enough, which will internally short circuit the battery, so then this will be the one more cause to failure of the battery. So this way, lithium plating again can be modeled. And then the last case study which we want to present in front of you, which will be the combination of two failure mechanisms. So in these failure mechanisms, what we can see gas evolution at positive electrode and lithium plating at negative electrode. When both things will work in parallel, and along with that, you can see the SA formation also. So which will risk. So we have a lithium plating, SA formation, and gas evolution, everything happening all together. So this homogeneous Newman's model in 1D can be modeled, and we can see the risk of guessing and and that's a formation. So this particular graph one that you can see is telling you that at what location you are having the guessing available in the cell. So we have the guessing is a reversible phenomena, but still it may be slightly irreversible, and we can start seeing the losing loss of material. And plating generally see at 0 volt, because it's a lithium particle which is we are dealing with. So then you can see the lithium plating as well, which is a reversible phenomena in the battery and battery pack. So we talked about four different kind of case studies where we see if there is any failure mechanisms, how they can be incorporated, and when it will go to the pack level model, how they can be handled. Now, when we come out from the cell level model, so now we go to the pack level model, where we may be interested to know that if you want to do the thermal management in the pack level model, why they may be requiring. So in some cases, when you are operating your battery at very high C rates, then it will produce heat. So we wanted to cool down the battery to avoid the excess heating, which will enhance the SI formation and the gassing. So it will slow down the deterioration when we want to do the cooling part of it. In some cases, battery is working fine, bed temperature is good, but still you will form some hotspots which will lead to the acceleration of the aging and then increase the risk of thermal runaway. So either it is cooling of the battery or identifying the hotspots. We in the both cases we want to cool down the batteries by adding the heat transfer to it, and the combo of battery modeling and the heat transfer will give you the complete picture of this cooling and the hotspot formation. In some cases, when you are operating at low temperature or the cold environment, then in low temperature operational, it may lead to the lithium plating, and low temperature also lead to the less electrolyte conductivity. That means performance also will be very poor. So now you want to start the battery. So then we will be starting battery from the very negative temperature, and then from there we want to bring the battery at optimum temperature where it performs well, which is the 30 degree to 40 degree. So this startup from the cold environment also one of the scenario which we can see by adding the heat transfer to the battery modeling. So the startup scenario, hotspot formation, and cooling, all three can be the possible operational condition. And in some cases, when we are fail to avoid the runaway, then in this case we will see the maximum temperature and avoid thermal runaway. So once we know and we will be able to replicate the behavior in worst case scenario of thermal runaway, then we can design some strategies to prevent the thermal runaway. Now we talked about the heat transfer. Then heat transfer can come in pictures into three different ways: conduction, convection, and the radiation. So in conduction, we can assume that battery is in solid and fluid. So then conduction can happen in solid and fluids, and the property is also known as tropic, so which can be seen in the jelly roll kind of scenarios. So we'll model the porous electrode thermally. Equilibrium or non-equilibrium also can be maintained in porous medium. So conduction includes the properties and the type of medium and the phases that we are dealing with. So solid comes fluid, porous medium, and the properties also not symmetric. So conduction comes in picture. But when you want to design the cooling mechanisms, then advection, which will be the conjugate heat transfer, can show up. So then you can do the advection part as well. And in some cases, if you are interested, which is very rare in the battery modeling, the radiation part, so then you can add that as well, which will be surface to surface and surface to ambient. In some cases, your radiation also help you to cool down the hot environment or hot surfaces. So then you can design the surface to ambient conditions as well. So, which losses will couple batteries and heat transfer? So here you can see we can see the joule heating, we can see the electrochemical reaction, heat of the mixing. So all three losses we can see and then plot them separately. So once you know which losses are dominating, then we can work accordingly. So let's say if your joule heating is more, that means the conductivity of electrolyte and the solid parts that we are working with are less. So then we can work on the joule heating part of it. So in joule heating, in joule heating, when we work on material part, or else we can design some very thin structures, so that we can provide this kind of joule heating scenarios. So in cases when your electrochemical reactions or activation of potentials are higher, then we can work on some catalyst part to avoid that kind of scenarios from the fundamental level. So and then heat of the mixing also can give you the local gradients because of the concentration. So this way, all heat losses can be plotted separately, and then based on the different separate losses, you can make some conclusions that how that can be handled. So, but our observation says that we can see the activation and the heating loss are the dominant forces in the batteries. So now we just take one case study from the thermal runaway scenarios in the cell level. So in cell level, what we can see the different kind of reactions that may get triggered, and they may be driven by the Arrhenius laws. So when you go for the high temperature, the reaction will become more violent. In that case, decomposition reactions, which are typically exothermic, they will be moderate. And then, based on the those kind of reactions, then we can see the failure, and that may cause the fire and even the explosions in the batteries. Thermal runaway, then that can be extended to the pack level model, where let's say we have a 24 cells in series and parallel, and then you can just give the exothermic reactions and incorporate the heat transfer to it. Then we can see the propagation to the nearby cell. So let's say one cell is getting exposed to the internal short circuit and external short circuit, or due to the excessive heating. Then how this propagation will happen in the pack, that will help us to mitigate the thermal runaway scenario, and we can design that thing in detail. Okay, so how that can be handled? Then this will be done by the thermal event. So the people who are seeing console first time, this is a GUI that you can have. In this particular GUI, this is the interface called designing for the battery pack. In this battery pack, we design the batteries and the heat transfer, couple them, both of them, and then we can incorporate the thermal event. In thermal event one, we say that it's a time waste where we know that this particular battery is getting filled, and then there can be thermal event two, which will be temperature based. So when one battery is getting filled, then how that will propagate to the other cells, that again can be modeled. So this way we have the hundreds of cells, and you can track the thermal and the electrochemical performance of them individually. Okay, so now this is the typical geometry which is used for this kind of simulation, where we have a cell holders, and then the packing cells. This is 2100 cell, and they are arranged in series and parallel, and the thin plastic wrapping also included here. And you can see the how this temperature or the heat loading can be done. So then this is the heat loading that we have given for the combustion reaction. Now, how this particular model is set up. So first cell is getting filled at one particular temperature, which is T start, and this cell is getting discharged at 2 C condition, and the initial SOC is 25%. First thermal event will happen at explicit time, which is 1 minute on one cell, and then it will exceed to the 80 degrees Celsius, which will propagate the thermal runaway to the other cells. And then we can add the ohmic resistance to the battery to increase the event in the trigger. Now, when we go to the heat transfer, then the properties, as I said, that it may not be the isotropic. So then you can provide those another property which are not symmetric, and then this can be done by the cooling by convection. So two-way coupling has been done. So heating is due to the Joule heating in conductors, electrochemistry inside the cell, and the thermal event. So three different kind of heat sources will get triggered once you have the battery and the battery pack coupled with the thermal systems. Okay, so now when we see one this particular pack will fail, so this is how we can observe the scenario. So what we can see, the first battery going to the thermal runaway, which will just increase the potential, and then it will discharge the cell. So this is the temperature which you can see. So first runaway happened, and then temperature reached to the 350 degrees Celsius. And then this is a second thermal runaway happened, and second trigger happened, and then there is a consecutive failure happening, and then ultimately it will go to the thermal runaway and it start cooling. So we can observe the T max and T average. So T max, which you can see, is triggering very sharply, but T max increasing is very gradually, and we can reach up to the same temperature where T max is reaching. So T average and T max both can be handled, and then you can see the failure of this battery by having the battery potential. So battery potential is increasing with the failure, and then ultimately it will drop down and die off. So this way we can see and observe that what was the pattern of the failure of our cell. So that can be seen in this kind of animation. So now first cell is getting failed, and because of that, you can see it is getting propagated to the other cells, and we can identify what is the maximum temperature, propagation pattern. And now if you can do something about it to prevent this, then that can also can be done in this kind of scenarios. So we can have some kind of wrapping around it, which is can be faces materials, any filler material, or any different other kind of or decoupling this kind of cell when it is giving you the alarm of the failure. So then all those strategies can be taken, and you can design your thermal runaway scenario. So now, as a first second, you can see this cell is getting hot, and then it's propagating the temperature to the other cells. Now, let's just see one strategy to mitigate that kind of thermal runaway. So now we can just take the same kind of geometry, and now it is discharging by the 4C rate, and then 100% SOC it is having. So what we can have the cooling with two different scenarios: cooling with air and cooling with facial material. So now, first we'll see how that is formulated. So now we are using paraffin, liquid, and solid. So that is deployed as a phase change material. So now we have paraffin in phase 1 and paraffin in phase 2. So now, when the phase change material will get triggered, so it is taken from one of the article published, and the rest of material properties are remain same as a thermal runway model. So now, when you compare both cooling strategies, so when we have an air-cooled system and the PCM cooling, so in air-cooled system, you will see the maximum temperature is around 50 degrees Celsius, and when you have the PCM cooling or phase change cooling, then you have the maximum temperature is around 40 degrees Celsius. So there is a almost 10-degree difference that you can observe uh, due to the heating of the system. So we have two different strategies: air cooled system and PCM cooling, and that will give you the 10-degree lower temperature, and then it may help you to prevent the thermal runaway kind of scenarios. So now, we have the facial material available. So we have the temperature difference in the air cooled system and the PCM system. In air cooled system, there is a difference of 7.5 degree, wherein the PCM system having the difference of 3.4 degrees. So this again helping you to get that uniform temperature distribution. And how this uniform temperature distribution will help you? So where your when your BMS is operating this kind of battery pack, then it will not get confused due to this uneven temperature, and it will take the right decision to keep this particular module into the in the circuit or not. So then, when you have the exact information and the temperature is also uniform, then your battery and the BMS also may perform well. Now, this is also one cross-sectional view that you can see for the different two different cooling mechanisms, and see the temperature of the PCM at different cross sections. So now, this is the comparison between two different kind of strategies, and see the temperature distribution due to that. So now with this we can conclude that this particular system can or the module can handle the different scales and purposes, which will where we talked about today thermal runaway, and anti-torque was very concentrated on the thermal runaway scenario. And what we can see that it can handle all chemistries, which will be Nernst-Planck equation, Butler-Boltzmann equations, and from system level models to the battery pack level model interfaces are available. So this battery pack interface, when we talk about it, will give you the scenario where you if you want to make a huge battery pack, then it will automate the process where you just import the geometry, assign the domains, and with assigning the domains, you will be able to get the different kind of variables in the system. And here you can incorporate the internal short circuit, plating, and abuse condition, and the thermal management system to see the thermal runaway and thermal management in this scenario. So with this, I think I can just give you the one demo about it. How if you want to see that thing in software, how it will look like. So. So let's say then we will be seeing one of the model which is for the thermal runaway condition. So this is the we have some example model available there. So let's say we have this thermal runaway propagation model. Okay, so now we can see here this is the one pack that we are working with, and then those batteries are arranged in series and parallel in this kind of pack. So the GUI, which is very accessible, so we have a model builder, setting, and then graphics. Here we'll see the battery pack that are being modeled. So in this, we have the air, which is a filler material, acrylic plastic, and the steel as a bus bar. Now, when you design batteries, so then we can work design the all batteries, and then we can see the voltage losses. So voltage losses are appearing for the, all three kind of losses in the system. So then here you can see we have the eta IR, eta activation, and eta concentration. After that, then we will move to the thermal event. So in thermal event, what we assign that for the first battery, it is getting filled at T start. That means some temperature is assigned. You can add the ohmic over potential here, and then this QH peak is due to the combustion reaction. And now the second the thermal event which is happening due to the temperature. So now we have the maximum temperature which will trigger the thermal runaway in other cell. So now you can see other cells are at thermal condition, and the first cell is at the time condition. With this, then we can assign the conductors and the connectors with it, and you can monitor the or observe the individual variables for the losses. So then, if you want to account for the individual losses, then you can see that many number of variables will be available, and you can perform the different charge or cycling for the different C rates. So then you can change the C rates, and then you can run this cell at that particular condition. And then when we come to the heat transfer, so then battery layers again will give you the feature where you can assign the property which are not isotropic. So this way, and then other solids are also being modeled. With this, when you run this kind of cell, then observe the behavior similar to which we saw in the presentation. So you can observe the cell voltages. So how cell voltage is behaving at the different failure mechanisms, different SOCs that you can see, and the electric potential while operation. You can see the temperature profiles as well. So these are temperature profile at around the cell, and then we can create the animation for this scenario. So now we can run this animation and see the propagation of the thermal runaway in this battery pack. So this is the one a brief intro that from our side. So now I think we are now open for the question and answers. And before that, I think we have one poll that we can launch. Now we can start taking the questions.
I'll just launch the last poll question.
Yep. Thanks.
Mhm. So I'll just request you to stop the screen share for the poll to be visible on screen.
Yeah, sure.
Thank you. Yes. So I would request the audience to kindly post their question and answers in the Q&A box here. Right after this poll question, we'll be taking the questions. Okay. I think we can take the questions now. I'll just screen one of the questions here. So your mic is switched off.
Okay, yeah, sure. So I think when you are talking about the thermal behavior in sodium cells, so sodium cells are the extension or the newer version of the batteries where instead of using lithium, we are just using the sodium ion. But when we talk about the modeling of those kind of batteries, so they will be solving the same kind of equations, only the size of ions will change. So now losses will be the same, but in the different orders. and the problems that you will face to conduct those ions will be different. Then same equation will be solved, and then they can be coupled with the thermal management system, and we can see the thermal losses due to the those kind of cells. So when you talk about the behavior, they will be pretty much similar to the lithium ion, but they will be a bit higher than the lithium ion batteries. There's a question: how do you model reversible entropic heat? So when you talk about reversible entropic heat, so some of the losses which you can see, they're reversible and irreversible. So let's say we are talking about the losses which are reversible in form. So these are the losses which we can be. Let's say we have the electrochemical reaction, which where the reversible in the manner. So when we talk about thermodynamics, so they are already accommodated there in the Nernst equation, and you'll be able to account for the reversible entropic heat generation. So if you will be more specific, then we can talk about those losses as well. So there's a question that foam combustion is possible during thermal runaway. So yes, if foam, that means let's if you are having filler material which is foam, and if you want to account for the combustion reaction, so this will be one more chemical which you want to see the combustion. That means you will model those non-phatic reactions. So then that is a straight chemical reaction which you want to model, and if you want to account for those combustion reaction and heat generated due to that, yeah, so that can be modeled and incorporated there. So here we just deployed one function for the heat generation due to the combustion reaction, but if you want to account for them, then you specifically model those chemistries, get the heat sources from there. So next question that we see, so is there any course based on advanced battery modeling from basic to expert? So yeah, so frequently we have the courses from the Indian offices and the global offices from US and the Europe offices. So if you're interested to know that those courses and the timelines, so then you can write us to the support@comsol.com, and then we can tell you the timelines and the dates where when we are having those kind of courses from beginner to the expert level. Yeah. I think there's a question that how the PCM density should be there in the back or the uniform heat transfer. So that depends. So let's say you can have the PCM which can be wrapped around the battery, and other places you are just having the different filler materials, or else you can entirely fill the cavities by the PCM, which will be very depends on the how much heat you are generating, and that affect the cost part as well. So there is a trade-off between the cost and the amount of heat which you are generating. So if you are working at a low shear conditions, then you are not generating much heat, and then wrapping the PCM around the batteries will be good enough. But if you are generating huge amount of heat, and then your cost is also allowing you to have the filler material in the cavity, so then you can have the very dense PCM filled into the battery and battery pack. Yeah, so let's just take one more question that so suggest me the best process once the cell and the module is got fire. So let's say you want if you want to know the process that how this failure is happening. So first, then you are at a cell level. In a cell level, there can be multiple failure mechanisms that can get triggered. So you model those things and identify your working conditions. So if you are, let's say, if you are at low serial conditions and temperature is also good enough, when high enough, then you don't have to worry about lithium plating. But in case you are at higher temperature and high serial conditions, then in that case you should be worried about the gas evolution and the share formation. So based on your operating conditions, you can decide which failure mechanisms you want to address, and then at the pack level model, then when it catch fire, that means then you are only at the phase of mitigation or the reduction of the losses. Then in that case, as we shown you that PCM cooling or the liquid cooling, liquid based cooling, or is any a different mechanism which will prevent the propagation. Let's say you are designed, you can design some fuse which will cut off the batteries to propagate the failure. So all those kind of different scenarios that now you can take. So you are either you are at a cell level or pack level. You can design the effective strategies to replicate the thermal runaway and mitigate those kind of scenarios as well. Uh, yeah, okay. So, out of SI formation and lithium plating, which increases the internal cell electrical resistance. So, as we discussed, that particle cracking is the one more thing which can increase the internal resistance. And apart from that, let's say your electrolyte is being converted to the something which is not useful or which is not conducting ions. So that kind of Faradic or the non-Faradic changes in electrolyte also may lead to the increase in internal cell resistance. So that is very different from the SA formation, but still it will reduce the one fraction of electrolyte, and that will increase the ohmic losses into the in your battery pack. Uh, okay. So there's a question that while performing parameter optimization, will other parameter adjust themselves if we change one parameter? Okay, so then when you are performing the parameter optimization, then you are focusing on that particular parameter. Other parameter will be remain constant, and if you have that parameter as a function of parameter which you are optimizing, then they may get adjusted. But if they are fixed and they are you are providing one parameter or the number, then they may be remain the same. So they may be highly subjective. Okay. So, do you carry out? So the question is, do you carry out this simulation activity as an outsource or self software? Yeah, so this particular company Comsol work on the software selling side. So if you want to know the if you want to get the solutions, then we are just providing the software, and then you can deploy your workforce and work with that. So, and if you want to contact with us, then again, you can contact us to the support at the consult.com to have the further discussion. Uh, let's take one more question. What are the advantages over active cooling and passive cooling? So when you have a active cooling, if you then it may maintain your temperature in the condition where the battery is operating safe, where you have a command over the cooling mechanism, because you can increase the flow rate of your coolant. But wherein the passive cooling, you have to depends on the external temperature or else the fans that you are deploying on the for the cooling. But in the active cooling, again, you are investing more energies to operate a pump. So then that is also one trade-off, and then that pump also will get operated by the battery itself. If you are using it in onboard application in a vehicle, then your efficiency also may go down. So then this way, active cooling having their own advantage, but then again, it may become disadvantages also when you are working at small scale systems.
So we have one more question left. And
Yeah. So the question is, after creating a cell model during console, how do we implement to work on the cloud platform? Like, okay, so if you want to use the cloud platform, so the console has tie up with some cloud platform where you can use their resources and work on a large system. But if your system is not large enough, then you can work on local PCs. But if still you want to use the large resources, then you can visit our website. There we have listed the cloud platform which supports consoles, and you can just submit your license there, and then they can help you to use their cloud platform for computational purposes.
okay, then
Uh, this question that can you give us an example about active and passive cooling? So when we say passive cooling, that means we don't have any active component like fan or the motor or the pump which is acting to cool down the battery. But when we talk about active cooling, that means we are having channels and some kind of active uh, equipments which is helping to cool down the battery. So that if you have any system which is actively operating, and you have command over that kind of active system, then that comes under active cooling. And then later another other part where you just depends on the external temperature or external ambient condition, then that comes under the passive cooling.
Those were all the questions.
Yeah. Okay.
Yeah. So thank you so much, Dr. Rustam, for that interesting and insightful presentation. And it really shows the amount of questions and interesting questions we got, that your presentation was quite impactful and had great takeaways for the audience.
Yeah. Thanks.
Okay, so with that, we have come to the end of our question and answer round and end of the webinar. A big shout out to our attendees for extending your time and support for the event. A special thanks to our partner Comsol for extending their immense support to organize this event. We promise to be back soon with another exciting session. The floor is now open for networking. Thank you all.
Thank you.